Recording in
All
progress.
right, folks, welcome back to our conversation about thermodynamics, specifically this entity in thermodynamics that's a little bit new to us called entropy. In our last video, we discussed kind of like the universal and then also the very micro scale definition of the second law of thermodynamics and how we can express that using this thermodynamic entity that is entropy. And we left off with a definition of the change in entropy of a chemical system, which relates to the enthalpy of that system and the temperature the system exists as, expressed in joules per Kelvin. So I've called this slide entropy is a state function because I want to remind us about what it means to be a state function in the first place. So this is the definition that we saw in our prior slide, right? The change in entropy of a chemical system, meaning from reactant to product, is equal to the change in enthalpy of that chemical system or the heat of that chemical reaction divided by the temperature at which the reaction occurred. So we can re-express this knowing that heat is conserved between system and surroundings, meaning that any heat that leaves the system is absorbed by the surroundings, and any heat that is absorbed by the system had to come from those surroundings. So then we can use this to re-express our entropy equation in terms of the change in heat of the surroundings divided by temperature over, sorry, not over, times -1. So we're flipping the sign because all of the heat that leaves or enters the system is the equal and opposite amount as leaves or enters the surroundings. So let's see here. What does this mean? If delta H surrounding, oh, hold on, I think I have a sign error here. Let's see here, let's go back. So let's see here. We are looking at entropy as being the change in heat of the system. Okay. Oh, I think, okay, we're going to start with a convention by assuming we've got some kind of exothermic system. So here's what we're doing here. We are saying that delta S cis can be thought of just like a change in enthalpy. So a state function, a change between states, is the same as the change in the universe minus the change in the surroundings. And we also know that at constant pressure, the change in enthalpy of the system is equal to the change in enthalpy of the surroundings. And if we're talking about exothermic, then we had assign the negative sign to our change in system, which means that if we wanted to consider how the universe has to always be increasing, then we arrive at the following equation, which was the one shown, but with a negative sign. So we've got delta S of the surroundings is equal to negative delta H of the system over T. So going back here, if we're talking about system, that is heat of system. And if we're talking about the change in entropy of the surroundings, which relates to the universe, then we got to just make this negative. So it's a question about system versus surroundings. So this is an expression of the change in entropy of the surroundings, because if the entropy of surroundings is increased, then we are increasing the total entropy of the universe. So this is another way of expressing entropy, knowing that this is following the second law of thermodynamics, which states the entropy of the universe is always increasing. So let's talk about this relationship in signs. So if the change in enthalpy of the system is, and let's fill this in, negative, this is where we are exothermic. So heat flows from the system to the surroundings. Then that also implies that delta S surroundings is equal to negative times the negative delta H cis over T. So the change in entropy to the surroundings is positive or increased. So this would increase the entropy of the universe. Let's do an analysis for if we were an endothermic. So if we are an endothermic reaction, then heat flows from the surroundings to the system, meaning that the change in entropy of the surroundings is equal to negative of the heat of reaction divided by T, which results in a change in the entropy of the surroundings that is negative. So it decreases the entropy of the universe. And the only way that this is something that is legal is if, as a result, the surrounding entropy is decreased, we have some like overall change in the entropy of the system that allows for the universe to obey the second law of thermodynamics. It was a bit clunky, so let's maybe practice this. Okay, let's see here. Do I have room on the next slide? No, so let's make a duplicate. Okay. Yeah, okay, I'm covering all my secrets on this slide here. Okay, let's now cover this up. And then let's call this slide practice relating enthalpy and entropy. So practice relating delta S and delta H. So for example, consider the combustion of propane So this is the reaction C3H8, propane gas, in the presence of 5 oxygen gas molecules reacting to form 3 carbon dioxides and 4 water vapors. We know that the heat of reaction is negative 2044 kilojoules. And let's see if we can't figure out A, what is the sign of the change in entropy of the surroundings as a result of this combustion happening? So I'm going to rewrite here, delta H is equal to negative 2044 kilojoules. Okay, just kidding. So what is the sign change in the entropy of the surroundings when this reaction happens? So we can use our definition of the change of entropy of the surroundings being equal to the negative of the heat released or exchanged or absorbed of our system over temperature. So here, since we are indeed exothermic, this is going to imply that delta S must increase in the surroundings. Okay. B, does this make sense? Is the entropy higher post-reaction? So let's consider the reaction itself. I start with, on my reactant side, a propane and 5 oxygen gaseous particles. So that is 6 gas molecules. This is my system. And then remember, our products are what we consider like the resulting surroundings. So like the product, the post is the surrounding, and then also everything else around it. And afterwards, we undergo our combustion. We've got 1, 2, 3, 4, 5, 6, 7 gas molecules. So the surroundings entropy is greater than the original entropy of the system. So therefore, the change in the entropy of our system, excuse me, of our surroundings, is positive. We have to have increased our disorder, and we did in this combustion. And then let's figure out what is the value of this enthalpy change at 298 Kelvin. So let's remember the units of delta S are in joules per Kelvin. And this is typically, our enthalpy is typically in the unit of kilojoules per mole. Here we are reacting 1 mole of propane, right? So we can treat this as just net kilojoules because we've reacted the 1 mole of propane. So we can now say that in joules, 1, 2, 3. So that's going to be delta H. Reaction, or the heat of combustion, is negative 2.044 times 10 to the 6 joules, because I had 1, 2, 3 in the thousands of a kilojoule. So 1,000, 1, 2, 3 times kilo, 1, 2, 3, 1,000 is 6. And since we're looking at this at 298K, we would get the change in the enthalpy of our surroundings is equal to negative 2044 times 10 to the 6 joules per our 298 Kelvin. Okay, we should get a positive value here. Let's check. This is 2.044. So 2.044 times 10 to the 6 times -1 times -1 divided by 298. This gives me 6.859 or 6.86 kilojoules. Notice this is positive, so this agrees with B. And this means that this reaction is going to result in the surroundings increasing in entropy. So this is an exothermic reaction, and it is also one that will increase the entropy of our surroundings, right? Increase the disorder of our surroundings. So we are being both thermally dissipating in our energy, right? And then also like structurally, we are dissipating our like concentration of disorder. So if we had to predict whether this was spontaneous or not, we would probably say yes, but there is a way to prove it. So in our next video topic, we're going to talk about this idea of like, what is it that actually makes something spontaneous? Because right now we have an idea that perhaps it's something relating to entropy, but we can't leave enthalpy out of the equation entirely. So we're going to craft like our final term in thermodynamics. It's going to allow us to explain what kind of energy, like the name of that energy, and how it's exchanged, and how that type of energy exchange is what is behind the explanation of spontaneous processes. So spontaneity and our last thermodynamic entity known as free energy is coming up in our next video.